Good morning. Suppose we have a circuit like this, which is balanced, and we are asked to calculate the currents here, the voltage at the load side, VAN, VBN, VCN. If it's symmetrical, we have to calculate only the voltage at one phase. We are asked to calculate the power delivered by the sources and the power absorbed by the load, which is here. So I think here the capacitors are connected in delta. We have to transform this into a star connection, the equivalent star connection, and then we can work on one phase to calculate the currents. The circuit will look like this now. It will look like this. So it means that we can work on one phase, and the rest are one phase, and the rest are there is a phase lag of minus 120 degrees between phase 1, 2 and 3, and here A, B, C. So what we have to do now is calculate first the current I1. Once we have current I1, we can calculate the voltage VAN, and we can calculate the power delivered. We can calculate the current IA, and then we can calculate the power absorbed by the load. So to calculate I1, we need to calculate the equivalent impedance of the circuit, which is ZA equivalent is 4 plus J3 plus minus 12J, and in parallel with the load, which is 10 plus J15. Let's calculate now. 4 plus J3 plus minus J12 times 10 plus J15 over this plus this is 10 plus J3, and we can write it in polar form. Plus 12 minus 90 degrees times this in polar form is 18 is 03 and 56 31 degrees, and here we have 1044, and argument is 16.7 degrees. So we can say that this is equal to 12 times this over this, and it's equal to 4 plus J3 plus 20 point this times this divided by this is 2724, and argument this plus this minus this is minus 50.39 point. I'm sorry, here we write point. Okay, so we can say this times cosine this is 13.213 minus J 15.97, and we can say that the equivalent impedance is 17.55 17.2 13 minus J 12.97, and in polar form is 21.55 minus 37 degrees. From there we can calculate I1 via V1 over Z equivalent. V1 is 240 0 degrees over 21.55 minus 37 degrees, and it's 1114 plus 37 degrees. So it means that our circuit is capacitive. Calculated I1, we can calculate now VAN. VAN is equal to Z, this impedance, which is here, times the current I1. So V1, let's call it ZA times I1, and ZA is equal to 20.724 minus 50.39 times 11.4 in and 37 degrees. This will give us 231 and minus 39 minus 37. This will give us minus 13.39 degrees. We calculated VAN. We can calculate the current IA. IA is equal to VAN over ZA. Is it right? Over VAN over not ZA. It means that the load impedance IA is equal to VAN over Z, the load, and VAN is 231 minus 1339.39 over Z load, which is here 18.03 56.31, and IA is 231 over 18.03. This is 12.81, and argument is 13.39 plus 56.31, and it's minus 69.7 degrees. So we have IA. We can calculate the power delivered by the source and the power absorbed by the load. So here we do calculations. S delivered, it's 3 times V1 times I1 conjugate. It's 3 times 240 times I1, which we have calculated for in minus 37 degrees, and it's 3 times 240 times 11.4 in, and it's 8020.8, and here is 0 degree minus 37. So it means that P 37 cosine times 8020.8. This is 6405 times 7 minus J 37 sine times 8020.8, and this is 4827 volt ampere. We can calculate now the load, the power absorbed by the load. It's 3 times VAN times IA conjugate. It's 3 times 231 minus 13.39 times the current IA conjugate 12.81 plus 69.7 degrees, and this will give us 3 times 231 times 12.81. This is 8877.33, and argument is 69.7 minus 13.39, and this is 56.31, and the power absorbed is equal to cosine times 8877. This is 4924.24 or 25 plus J QL. This is PL. QL is 56.31 sine times 8877.33, and this is 7386.4 vars. This is the load power, and this is the load delivered by the 3 phases. And if I haven't made mistakes, I finished for today, and thank you very much.